Quantitative fair wall questions. You feel comfortable having the test next week, or did you want to put it off? By one, we can only do one. I don't care. I mean, there's with 6. When a class gets big, I have to advance because it's basically just you get like a class of 30, you just have to say it is here. With 6 of the time.
The week after, that's what traveling with the volleyball team next week a lot of nights, so I won't have a lot of time.
Do you prefer to have it put off?
Yes, if everybody else is good. I agree. That's everything. I went back and forth to something.
That's again, when there's 6, I'm more flexible. When there's the class is big, you just can't because there's going to be so many conflicts. To move it is creates more problems than it's worth. And so when the class is big, you just have to say this time is here. Well, there's 6%. Okay. Okay. So it'll still cover the same things. All the magnetic fields. We'll get into waves next week. The first part of waves. We'll only cover the first part, which is the question. I think you'll like those. They're very mechanical. They're those quite beautiful. Okay. Well, that's done.
So wait, the third exam starts with this?
We may or may not get some stuff with waves. We probably will because otherwise then the file's going to do things up. So.
Are we doing the finals during finals week, or are we going to do it like we did last semester? That's fine.
We'll probably have it during finals week, just because we've lost enough time just with all this stuff, weird stuff going on. Okay, so quantitative. Very long questions. Okay, so let's look at a case like this. We'll start off simple, then we'll start with more complicated. Let's say I have, here's an XY plane. Oh, I created a new homework too. There's a new homework up on campus that will be tomorrow. So you can have access to it. Let's say I have a magnetic field going like this. This is some B, and it's constant, say it's 2 Tesla. And you have a ring in the XY plane. Actually, it's not going to be 2 Tesla. So it's like that. This is a ring in the XY plane. Let's give it a good radius. Let's say the radius is, let's say 2 centimeters. And I'm going to say that this magnetic field here is actually going to go like this. You look at the magnetic field versus time. It's going to go as this guy. It's going to go like this. And this will be 2 Tesla. Let's say that this is going to be 3, 4. I'll say that this is going to be milliseconds. Friday, I want you to find the direction of the induced current. Part B, I want you to find the induced EMF. And part C, if the ring has a resistance of 100 ohms, I want you to find induced. So does everyone understand the problem? You have XYZ axis like this, the magnetic field going up along the Z axis, and you have a ring. The magnetic field going up through here mirrors according to this. The question is, find the direction of the induced current, then the actual EMF in here, and then if you know the resistance of this ring, what's the current? Okay, proceed. Yes. Yeah, magnetic field. All forces. So far, that's correct.
Would the flex be decreasing in that direction?
Yeah, so here you have a ring, there's magnetic field going up through there, so there's flux going up through there. And what's happening to the magnetic field over time? It's decreasing. So what's the flux doing in this direction? Getting weaker. So what does Lenz's all say about this?
So the flux is getting bigger.
Yeah, it wants to oppose a change. So the change is that here's a loop, magnetic field going this way is getting weaker. To oppose that change, it has to create its own magnetic field going in the same direction to bring it back up to what it used to be. So this thing here is going to create its own magnetic field. I draw like the dotted lines like this. So this is B induced. And that's going to bring it back up to how it used to be. So how does that magnetic field have to go then? How's this right hand rule? Take your right hand. You tell me what to do now. Put it on your head. Go like, no. What do? You point your thumb in the direction of the induced B field. The induced B field is going up, so this is going up. Your fingers are up in the direction of the induced current. Does that make sense? Okay, it's hard to read everyone's face with the mask on. I'm hearing kind of dead silence. So I think there's some questions here. Ask away. Okay, so are you happy with here's your loop, and the magnetic field is going up through it. And the magnetic field the magnetic flux going this way is getting weaker because your magnetic field is decreasing time. You're happy with that? Okay, now what does Lenz's all state? Lenz's all states that the induced current is going to be set up in that ring to oppose the change. So if it's getting weaker in this way, to oppose that change, it wants to bring it back up to what it used to be. So it's going to create its own B field going in the same direction to bring it back up to that strength that it had before. So are you happy with the induced B out being that? Okay, now you have to use one of your Brazilian rings. So which one is this? This is going to be where you point your thumb or your right hand in the direction of the induced B. So your thumb is going up. Your fingers are up like this. That means if I had a ring like this, if I had a B like this, the current would have to be going like this. That's how you know this. Okay. Now, okay, questions? Now let's do the part B. Let's find the induced EMF. So what is Faraday's actual law? The induced EMF. Again, this induced EMF acts just like a what? A voltage. Okay. Equals minus the change in the magnetic flux with respect to time. Okay, now what is the magnetic flux?
The magnetic flux, we wouldn't be looking at the ring, it would be the field itself, yeah.
Okay, so what is this? Let's get this guy first. How do we define the flux? This is sum B dot delta A. So I'm going to draw two pictures over here. Again, this B here is going to be this B here. Okay, I'm going to do this, so we're going to use actual this B here. So when we actually do this, and how does this delta A go? Delta A is always, it's always outward and normal. Now the problem is if you have a flat sheet like this, what is outward? Is this outward or is this outward? Either could be outward. So what I would suggest doing is take this in such a way that it's pointing in the same direction as the B field. Just, you don't have to. That's just considered a mindset. So if I actually draw this here, I'll draw two pictures here. So here's a B, the external B field like this. This is B. If I draw a little tiny patch of area here like that, that's my delta A. If you do a, let's see what that's going to output here. If I do kind of look down on this thing like this, what would I have? Here'd be my x-axis, here'd be my y-axis. I have this here, I have all these. That'd be the V field here like that. But I give it a little circle when I was through that. So then I draw a little bit. That would be my delta. Okay. So there's two different views. This is kind of an end view looking down along here. So the V field is going out like this. This is a sine. Okay. Now let's work this out. How'd you do that product? Magnitude V. Magnitude delta A. Cosine of the theta, the angle between these two. So if A, delta A is like this and if B is like this, the angle is 0. Cosine of 0 is 1. Now, this is the flux at any given time. If you're to take a snapshot of this, is the V constant at any given time? It is. Okay, any given time, the V along this whole thing is constant. So even though the speed is varying with time here, that's okay. At any given time, when you do the sum, that V is constant. So I can actually pull that V outside of this sum. You tell me what this is. Of a circle, right? Because this is just a circle here, it's not a sphere. So you're just taking this delta and summing them up over the whole thing here. What do we get? Well, that is the circumference pi r squared. This is here. B pi r squared. Okay. Now I take this and put this into here. And if you look at the pendulum, if I go like this, I'm actually out of phase when I decrease. Now what can I take out of this? Pi r squared. So this is me minus pi r squared. Tell me what this is right here. Change in V with respect to change in time. In this case here, that's nothing but the slope of this line. This is your slope of the V versus T graph. So what is the slope here? Doesn't understand how come from home to this. Or she's a Roman mathematician. Too. My home not. So what do we have? What?
She have chalk to write this on?
No, the whiteboards as well. She would be called with chalk. That's why I married her. That's why she married me. We understand the problem. Okay, so what would that be? Almost. It's close to 2. Why isn't it 2/4? I'll give you a hint. 2/4 is this. We don't have that. What do we have? With that. We have -2/4. Again, how do you always do these changes? A change is always a what? Final minus initial. If you'd actually do this, what do you get? You got the final value is 0. The initial value here is 2. Over the final t is 4. The initial t is 0. Okay. So this is -1/2. That's what goes in here. But if we work this out, hold on, got minus pi r squared times -1/2. We got 1/2 pi r squared. What was our r? 2 centimeters. Okay. So this is 2 times 10 to the -2 squared. What would be the unit for this? Yes.
What is it?
Okay, which one?
It's like as soon as we figured out that
Which one?
delta B over
This
delta
guy?
T.
Oh.
Yeah, as soon as we figured all that.
Okay.
I had no idea.
Okay, so once you have this, we just put it into the thing. So are you happy with the fact that, are you happy with this equation?
Yeah.
Okay. So the pi r squared is a constant. So I can pull that outside of it. So I can do this. Now I have this delta B over delta T. So in other words, how the magnetic field changes with time. And that's what we get from this graph here. Right? And so we calculate the slope here. So you have the slope being -1/2. All right. You look at how much did we change this much? The change by -2.
Okay.
The time was changed by 4. We take the change of b -2 over 4 plus that. That makes sense to you?
Yeah.
What are the units for this? What did I say this acts just as? A voltage. So the units for this are is a volt. So this would be this many volts. Okay. Last part, yes.
Where is the 2 times 10
Because the SAR, it's 2 centimeters, wasn't it? It was 2 centimeters. And so you have to convert this on to MPS units. So this is 2 times 10 to the -2 meters. Okay. Oh, damn it. I'm sorry, darn it. Can you tell me why I'm missing a factor of 1,000?
-3.
Where'd it come from? What is the time?
Seconds.
Yeah. Is the time 4 seconds? No. Time is 4 milliseconds. So, well, watch what I can do because I have this for technology called marker. Okay. Because a millisecond is -3. So I can write this as times 7 minus 3. So this is going to be this is going to be -500. Make sense? Sorry about that. So for this in here. Okay, now tell me what the current's going to be. Yeah, for part C, we know that V is I. Oh, I better use a different R. I call it R, like I use the lowercase R. So your I induced. It's gonna be this V over R. That's really just our script V over R. So that's this fellow here. Over the star of 1,000. Over 100. And that would be your I induced. We'll call it star. Maybe the units for star? Which is the correct? That makes sense? Oh, I think the resistance was 100, wasn't it? Was it? That's something I remember. Okay. I want to show you something. We're going to be able to feel. Has everyone been shocked? Electricity? Been kind of shocked with electricity? You're going to get shocked. I mean, okay, if you want to be shocked. This makes sense? Okay, let's try another one. Let's have a B field like this. This is a B field. And I'm going to have a loop. I'm going to do this is going to be a side loop. This is a little hard to draw. I have a side view like this. I'm going to have a loop like this. Here. And here's basically the axis, and I can kind of rotate this around here like this. So if I did a kind of end view, what I'd have is something like this. Let me kind of illustrate this. What this would be, imagine I have my magnetic field going straight up, and here's going to be a rectangular loop here. So imagine I have a wire like this, and I have some axis here. And I can rotate this like this. Okay. What I want you to do is I want you to find. Let's go some values here. We're going to call this L. We're going to call this W. We're going to rotate a loop in a magnetic field. And let me go in this one. What do we do with that? Oh, my goodness. Why would this be a Faraday solve problem? I just have to let the flux for this. Know the magnetic flux is a cell on B. How's I thought they have to look there? What does our delta A do? It's outward and perpendicular. Now we can't really do it now because it's flat, so there's only it's 2 ways to be outward. So if here's my piece of paper like this, what would then my delta A vector look like? In other words, here's my how that look? So I want the flux going through here. That's my delta A vector look. It'd be like this. Delta A vector. We have to be like that. Does that make sense? So let's say this is an angle theta. What would be my flux then? That product is E times magnitude delta A times cosine of theta, which in this case is just cosine of theta. Again, remember, this is done at any given time. Suppose I want you to now, what could you pull out of this sum? B would be a constant, so I pull the B out. At any given time, what else would be constant? Yeah, it'd be this cosine as well, cosine of theta. And I have this guy here. And what would this quantity here be? Yeah, it has to be the area of that loop here. So the area of the loop. In this case here, it just says the outcome sum. So this is outcome sum. I could write this as outcome W, and good B, cosine theta. Okay. Does that make sense? Now, what would this theta be? Remember, this is out for handle, and I can crank it like this. In other words, what we're going to find is this could be like this, I can crank it like this. I'll try to convince you that there's a whole bunch of if you're rotating this omega here, this theta here is actually going to vary with time. So if this is rotating like this, it turns out that this omega here, this theta here is going to be some omega times time, and this omega here, this is the number of revolutions. In other words, this omega here is delta theta. Remember from first semester of physics. Okay. So if you were to graph this, what would you get? How's that look? This is a constant. This cosine is really going to be cosine omega t. So really what you're going to have here is you're graphing this B omega cosine of theta, but that's really just for B LW cosine of omega t. My W is an omega, so look too much alike. So if you're to graph this, this is going to look like this. Does that make sense? So what does that mean about in this loop here? How's the current going to go? This current's actually going to vary. So if you go to calculate this guy here, that's this. You put this in here. What would come out of that delta here? What's constant? Yeah, the B is constant, the L is constant, along with the W, and this would give delta, the change in cosine omega t with respect to term. That's just going to be the slope of this graph. So really what you're going to be doing is having something that varies with time. What does this produce for you? So what's the slope right here at the front? That is 0. The slope here is 0. The slope here is 0. Here's the slope is a maximum. If you're to graph this, this right here. This is cosine omega t. This is delta cosine omega t. This is just a slope of the cosine omega t versus t graph. Slope here is 0. Slope here is 0. What you have if you graph the other spots, we're going to get something like this. So this is just variant. So what do you think we just produced? What? This is alternating current. This is actually how you make alternating current here, professionally. So what you do, I'll pass this down. Okay, in this case here, okay, you have a whole bunch of horseshoe magnets here. Now you can't really see, you can actually have to look in here. If you turn this, if you over here and look in here, as you turn this, you can't see it because these loops here are wrapped in a kind of some sort of insulating layer. And what isn't obvious is that when you actually turn that handle, it turns out there's a loop like this, it turns out there's loops like this, a loop like this, a loop like this. There's a whole bunch of loops here that you're changing. So what happens is when you turn that handle, you're changing all those loops at time like this, and then it actually increases the voltage. And so if you have any type of power plant like you have, is you basically, they all come down to the fact that you're going to have a whole bunch of loops that spin loops in a magnetic field. That's how any power plant works. The question is just what source you use to turn the wheel. If it's hydroelectric, you have waterfall, water falls through, turns the turbine, and all it's doing is spinning loops in a magnetic field. If you have a coal burning plant, what are you doing? You basically have coal, you burn it, use the heat to get steam, and then the steam goes and then turns the turbine. If you have a nuclear power plant, what do you do? Well, the nuclear plant that boils the water, and then that steam is then used to overturn the system. So any type of power that we have comes from basically a big scale produce. You can see this with the tiny little window, okay? And go with this, okay? This is actually kind of hard to turn. Now, it's tapped off here. What you can also do is if you want, you can actually put your fingers here. So instead of the current going through the light bulb, I haven't tried to hear the light bulb, so I'll go first and see what it's like. Oh, okay. So you can do this. Okay, so you don't. Okay. This is not, I'm not going to hang. Yes. If you want to shock you, it's a quick thing. Put your fingers here. And then turn this like this. And to go kind of light, it's not going to be much. If you do a little bit more. Okay.
How does the steam make the current? Like, what do they do with the steam?
The steam is just used to turn a turbine. So you have the turbine that the steam head basically has the steam going through it, turn the turbine. It'd be like going through something. Your fingers here, unless you don't have to. We won't take your 1 feet. That's fine. Okay. No, I don't think we're. Yep. Okay, so in other words, when we spin it like this, we're spinning it, we're actually changing it this angle with effect of time. That's us. So it's however fast you're cranking that. So this omega would be depending on us, depending on what you're doing. So if you do it lightly, like this angle is changing over time. If you're doing it a lot, then this is actually going to put. Yes. Which part here? So this and this are all constant, so I can pull those off. So this gives me the minus change in cosine omega t with respect to time.
So that's cosine.
Yes.
Okay. What did you write there? This is like E of the cosine.
Yeah. So this is our flux. And then we took that and put it in here. Took this and put it right in there.
Yeah, I get it. But like it's cosine what? It's
Omega t. Or theta here is omega t.
oh,
Does that make sense? Okay. Don't worry too much about going from this part here. I just want you to see where our power comes from. That's exactly how we get it. It's just on a much bigger scale. Okay, so when you have a wind turbine, what does a wind turbine do? If you go up there and I should look at the turbine, what is it? It's gonna have a whole bunch of loops, basically in a magnetic field. And you're just using the wind to basically, instead of you cranking it like this, the wind is turning the turbine and turning the loops. What? Oh, okay, this is, okay, the second off, this is kind of cool. So we're gonna have a chance to do this second one? Yeah, okay, you can try something actually different here, because it's kind of neat. You can do this, nothing happens. And then kind of hook this up here like that. Yeah, a little finger there. And then try to do it like this. It's actually a lot harder. So in other words, I go like this, I actually have to look at it. This is out here like this. That's actually a lot to do. How come? Okay, because what I'm doing in this case here, I'm actually, when I'm going like this, I'm just doing this out here. When I'm going through like this, and sending current through here, there's a power loss here. I actually have to supply energy to actually have power loss here. And so there's actually the fact that there's a load out. This is called a load here. You will actually sense it in there, because it's actually not when I'm turning it like this, I'm just not turning wheels. I'm actually sending current through here. There's going to be a power loss here. And a power loss that's coming from somebody. It's coming from me. That's why I have to crank it. It's actually significantly harder. Now you can still go like this. Well, yeah. The only person who died was, and Jimmy was frankly, remember Jimmy? I got burnt right here on the big buck teeth and stuff like that. I asked all those irritating questions in class. So, it's sad that Jimmy got a lot. Sometimes happens. He also lost his hand basically from a crocodile tap out. Foster like.
A lot of, because in high school, I took physics, and like, every time I was getting exams,
Jimmy just always, he just said that. So sometimes that happens with students, and Jimmy just did not have good luck. What? Okay, so there's a little. Okay, first of all, turn it off. This is going to work. Okay, but if you have, okay, just kind of went through this. Okay, any questions on it? It's kind of neat. Yeah, let's try another one. Yeah, I think we can do one more. Let's say this is B, this is uniform. And here's a loop. This would be L, like this. And this whole thing here is W. Okay. The question is, for part A, find direction of I induced. For part B, find the flux. Part C, and this. There'll be more parts where we'll do the other parts tomorrow. Okay. You tell me what that is. You see, you have to turn it a lot harder. Yeah, I mean, if you look, you're getting the light. It is lighting, but notice how much harder it is to do. Thanks. Okay, when I was growing up, my parents had one of those old-fashioned phones with the crank like this. Okay, this is my favorite toy growing up because basically it wasn't connected; they just had more as a decoration. But if you open it up, it had all the working parts. And they actually had there's a little that when we turn it like this, there's actually a little generator. I had so much fun basically putting my finger there and then shocking my friends and shocking each other and stuff like this. And it was fantastic. It was just wonderful. It was like the greatest toy ever. I think every house knows it. I still have it. Okay. It's fun when you're 7, 8. It's cool.
Yeah.
So now I know. It's just brings back fun. The halcyon days of youth. Okay, so how do you do this? Which way is it? And we're going to move it this way. It's going to be moved into some constant velocity like this. Okay, so the magnetic flux going in here is increasing. So the induced B field has to go how? Has opposed to change, so this is B induced. Keep going. Yeah, so you point your thumb in the direction of B induced, and then your fingers are up in the direction of the current. So the I induced is like this. This is I induced.
Right, okay, so.
Okay, are you happy with that? If you're pulling it in like this, there's remember magnetic field going in here. Remember what magnetic flux is. That's your magnetic flux. So what's happening here? The B isn't changing, but you're getting more and more of the area in here. So that magnetic flux going this way is actually increasing. Does that make sense? Okay. So what is the change? The change is that the magnetic flux going in here is increasing. So how can it oppose the change? It has to create its own magnetic field going out to basically bring it back down to what it used to be. That's opposing the change. And then how do you get that current? You point your thumb in the direction of the induced, and your fingers are up in the direction of the current. So you get this thing here, like this. Make sense? Okay. Now, tell me how to calculate this. We'll do this part and then we'll calculate some of it. This is magnitude B, magnitude delta A, cosine of the angle between the two. How does our delta A vector go? So here's my B. How does my delta A vector go for this? So it has to be perpendicular to this guy and outward. Since there's no outward, if you just have a flat sheet, I'm going to take my delta B to go in that same direction as this B here. So this is my delta. This is my delta A. So what angle does delta A make with B? 0. This is 1. What can I do with that delta B? I can take it out. Now here's the tricky question. What is this quantity here? It's only the area of the rectangle in the field. It's not over here. It's not the whole thing. What's the magnetic field out here? 0. So there's no flux out here. It's only this part here. It's only this part here that contributes to the flux. what do we get here? Let's call the section inside here and call this X. Okay, don't confuse this X with that X, they're different. Is that too confusing? This X is not that X. Because this X is like that, and this X is like that. If I meant that, I'd write that. When I say it didn't write that. I wrote that. See, they're different. We'll call it Y. Y. So Y is going to be the portion of this loop inside the field. So what's the area of this section here? So this is going to be the area. Inside. The area of the loop inside the field here is going to be this Y times L. Makes sense? We'll stop this problem here. We'll pick this up tomorrow and we're going to add some more parts. Okay, have a great day.